Let's just add a couple of more details to the cascades of the nitrogen cycle through the system. Deoxygenation or the eutrophication that I mentioned already several times is one of the big impacts of the unintended flow of nitrogen through the system. The circulation itself in the natural world creates these low oxygen regions. We won't go into the dynamics, but you can find plenty of literature on it, and especially in the Arabian Sea and the Bay of Bengal you have massive, very low oxygen waters, and they are hypoxic, anoxic, whatever. It depends on the concentration of dissolved oxygen. If it is less than about 5 milligram per liter, it's called hypoxic, and if it is less than 2 milligram per liter, pretty much nothing can live in it, then it will be called anoxic. And eutrophication is a word, usually U is a good thing, maybe not euthanasia, but eutrophication is where you have too many nutrients flowing into the coastal waters, and when there is light available, nutrients drive photosynthesis and phytoplankton blooms. In the natural system, phytoplanktons are grazed on or eaten by zooplankton, which are then eaten by fish, and then those fish are eaten by bigger fish, and so on. So this is the primary production in the waters that drive food webs, including in the lakes and so on. And when you have too many nutrients and the blooms get very big, the zooplankton cannot keep up and cannot graze down all that phytoplankton. Phytoplankton lives for a few days to, let's say, a month or so, dies and sinks, and below the water column, below in the deeper part of the water column, there are aerobic bacteria and microbes which then eat this dead material, detritus and so on, which use up the oxygen to consume this organic matter, and that is what drives the oxygen down. For example, here the Baltic Sea has the largest coastal water hypoxic zone. In 2011, the area of water with dissolved oxygen concentrations less than 2 milligram per liter was nearly 80,000 kilometers squared, and the Gulf of Mexico, which is really warm and some of the warmest waters at these latitudes, has a massive naturally occurring hypoxic region, dead zone it's often called, but the breadbasket of the US, which is on the Mississippi watershed going all the way to the Canadian border, washes in huge amounts of nitrate and nutrients into the Gulf of Mexico, which has been increasing the volume of hypoxic waters in the Gulf of Mexico. And all these coastal sites in red here are basically now largely affected by human activities in terms of agriculture on the watersheds that wash into these coastal waters. So European regions are full of it, America here, South America, Asia, and Africa as well, and so on. So this is obviously a massive problem, which is an unintended consequence of nitrogen cycle being perturbed by fertilizer application. But this is also being now exacerbated by warming of the ocean, which is related to greenhouse gas emissions, global warming, and obviously warmer waters have reduced solubility of gases like CO2 and oxygen. So deoxygenation is a big problem. So some deoxygenation numbers and effects here. During the past 50 years, the area of low oxygen water in the open ocean has increased by 4.5 million square kilometers. World's oceans are now losing approximately 1 gigaton of oxygen each year. So this is now a combined operation of nitrogen fertilizers on land, global warming because of greenhouse gases, and so on. If you look at this in another way, total fertilizer nitrogen in hundreds of millions of tons, and annual average temperature anomaly, you can see here population growth since the 1950s, nitrogen fertilizer use in 100 million tons, and cumulative coastal systems reporting hypoxia per decade. And this is the annual mean temperature anomaly. So the warming, the increasing in hypoxic coastal areas, nitrogen application, and population growth. So you can see that this has had a good impact on population and feeding the population, reducing starvation, but it is indirectly contributing and directly, as we will see with N2O, to warming and hypoxia in the coastal regions. The other aspect of the nitrogen cycle we mentioned is the production of NOx by fossil fuel burning in the industries and in the vehicles. Obviously we talked about NOx before, and volatile organic carbon compounds with heat and sunlight affecting ozone. So ozone in the troposphere is a bad thing. It's a pollutant, bad for health. It's a greenhouse gas. It can affect crop yields, and nothing good about ozone in the troposphere. So this is another impact of nitrogen cycle that humans are impacting through the non-fertilizer use. Where does N2O come from? So here it is. Agriculture and soil management contributes almost 75% of it. So that's related to fertilizer use. Nitrous oxide emissions of the US by source here for 2017, transportation, manure management, industrial and chemical production, stationary combustion, and primarily power plants that are producing nitrous oxide as well. Nitrous oxide is a very powerful greenhouse gas. We typically talk about it in terms of greenhouse warming potential, so we set that to be 1 for CO2. There are differences if you do it by weight versus molecules and so on, but without going into details, this is almost 300 times as powerful as carbon dioxide. But as we said before, it's the concentration that matters. It's the residence time, or how long it lives in the atmosphere, that matters, and its global warming potential that matters as well. N2O lives in the atmosphere for tens of years to a couple of hundred years, so not as long as carbon dioxide, but it's much more powerful than carbon dioxide. So if you quickly look at the N2O emissions from the approximately the Industrial Revolution, there is the CO2 increase, which is now well over 400 ppm. Methane has increased. Remember, these are in parts per billion as opposed to parts per million for CO2. Nonetheless, methane is 26 times as powerful as CO2 in its greenhouse warming potential. So also a bad news. Its residence time is about 12 years, as we talked about before, and N2O has also increased over this time. Okay, so this is what we have to worry about when we talk about nitrogen cycle overall. So this is a good example of how ammonium industrial scale production of ammonium did so many things, including the Green Revolution and allowing the population to be fed and potentially contributing to population growth. But it has had all these unintended cascades into the Earth system. So do you think of fertilizer use and fossil fuel burning to produce N2O as a unintended geoengineering project that has gone wrong? Or is it wrong to call such a mess unintended consequences of one thing affecting planetary operations as geoengineering at all? David Keith apparently disagrees with calling this as a geoengineering experiment, because he says engineers are not intentionally creating a mess. Unintentionally they may, but their engineering designs are always focused on efficiency, safety factors, consequences, and so on. So he would say, don't call this a geoengineering experiment, but the definition, of course, is that anything that we do at this scale that affects, including global warming, of course, CO2 and fossil fuel use, have done planetary scale impacts and affect the planetary functioning, Earth system functioning. So heuristically you can debate about whether these are geoengineering or not, but it gives you a metaphor for how geoengineering has to be thought of when we want to make sure that it's safe and it affects people in a positive way, and unintended disparate impacts are not enforced on people who are not contributing to the geoengineering or the global warming. Okay.